Hello and welcome. Do you want to successfully complete the D514 exam? Then you are in the right place. Our website has free questions and answers for the D514 exam. We know OA exams are tough, so our guides and practice questions are all free. With over 100 plus success stories, we have proven our videos will help you pass your exam on the first attempt. In this video, we will cover questions from healthcare statistics, database architectures, research methodologies, quality indicators, research ethics. So, let's get started.
Question 1. A healthcare administrator is reviewing patient records and notes that the dataset includes a column listing each patient's insurance carrier. The carriers include Aetna, Blue Cross, Cigna, and Medicare. Which data type best classifies this variable? Your options are A. Ratio data measured against a true 0 point. B. Interval data with equal distances between values. C. Nominal data used to categorize without order. D. Ordinal data arranged in a meaningful sequence. Which one is it? Pause the video if you need more time. The correct answer is C. Nominal data used to categorize without order. C is correct because nominal data assigns category labels that have no inherent order or numeric relationship. Insurance carriers are pure category names. The only meaningful statistic for this column is the frequency or percentage of each carrier in the dataset. A is wrong because ratio data requires a true 0 and supports proportional comparisons, like a readmission rate. Carrier names cannot be ranked against 0 or compared as ratios. B is wrong because interval data has equal numeric spacing between values, such as temperature in Fahrenheit. Carrier names are not numeric and have no spacing to measure. D is wrong because ordinal data carries a meaningful rank or order, such as pain ratings from 1 to 10. Insurance carriers carry no implied hierarchy. Nominal data sits at the most basic level of statistical measurement. The word itself comes from the Latin for name, and that origin tells you exactly what this type of data does. It labels, not ranks or measures. A nominal variable assigns each observation to exactly one category. Those categories are mutually exclusive and collectively exhaustive. Because the labels carry no numeric meaning, counting is the only valid operation, and mode is the only measure of central tendency that applies. Picture a hospital billing column listing carrier names. Each patient lands in exactly one bucket: Aetna, Blue Cross, Cigna, Medicare, or self-pay. The team counts occurrences and reports proportions. No one computes a mean carrier because that operation is meaningless. The most common exam confusion is between nominal and ordinal. Ordinal categories carry an inherent rank. Cancer stages or satisfaction levels cannot be reordered without losing meaning. Nominal categories carry no such order. If you can freely reorder the categories without distorting the data set, the variable is nominal. A classic trap is numeric coding, a specialty coded as 1, 2, or 3. Those numbers are pure labels. There is no arithmetic relationship between them. When a STEM tempts you to compute a mean from coded categories, recognize the variable as nominal regardless of how it looks. Question 12. A hospital is analyzing a patient satisfaction survey that asks respondents to rate their experience on a 5-point Likert scale ranging from very dissatisfied to very satisfied. Which data classification applies to these survey responses? Your options are A. Ordinal data because the categories have order but unequal intervals. B. Nominal data because the responses are simply labels. C. Ratio data because the responses include a meaningful 0. D. Interval data because the values are evenly spaced. Take a second. Which answer would you pick? The correct answer is A. Ordinal data because the categories have order but unequal intervals. A is correct because Likert scale responses have a clear rank order from low to high, but the psychological distance between adjacent ratings is not guaranteed to be equal. That places them firmly in the ordinal category, where order matters but spacing does not. B is wrong because nominal data has no inherent order, while Likert responses clearly move from negative to positive. The order is the entire point of the scale. C is wrong because ratio data requires a true zero that represents the absence of the quantity being measured. A Likert scale has no anchor zero, and ratios between ratings carry no meaning. D is wrong because interval data assumes equal numeric distance between every pair of adjacent values. A satisfaction scale cannot guarantee that the gap from neutral to satisfied equals the gap from satisfied to very satisfied. Ordinal data sits one level above nominal in the measurement hierarchy. Categories carry a meaningful rank, from lower to higher, or worse to better, but the gaps between those categories are not guaranteed to be equal. Classic ordinal examples include pain ratings, Likert satisfaction scales, cancer stages, and education levels. The order is meaningful and cannot be shuffled without distorting the data, but the psychological or experiential distance between steps may vary. A patient reporting pain level 8 is worse off than one reporting 6. That ordering is reliable, but ordinal data cannot guarantee that the gap between 6 and 8 equals the gap between 2 and 4. Unequal spacing is the defining limitation. The first exam trap is treating ordinal data like interval data and computing means uncritically. The safer summary is the median. The second trap is confusing ordinal with nominal, The clue is whether reordering the categories would damage the meaning. Watch for signal words like ranked, rated, stages, or Likert. Ordinal data guarantees rank, but not equal distance between values. When spacing between categories becomes uniform, the variable crosses into interval territory. Keeping that boundary clear is the central skill for measurement questions. Question 3. A quality improvement team records ambient room temperature in degrees Fahrenheit during each shift on a hospital floor. The team wants to know which data classification this temperature column represents. Your options are A. Ratio data, since temperature has a clear lower limit at 0. B. Interval data, since equal differences exist but 0 is not absolute. C. Nominal data, since temperatures are simply numeric labels. D. Ordinal data, since temperatures can be ranked from cold to hot. Before I reveal it, which one do you think is right? The correct answer is B. Interval data, since equal differences exist but 0 is not absolute. B is correct because Fahrenheit temperature has equal numeric spacing between values, but the 0 point on the Fahrenheit scale is arbitrary rather than the absence of heat. That combination defines interval data. Means and standard deviations can be calculated, but proportional comparisons cannot. A is wrong because ratio data requires a true 0 that represents none of the quantita. 0 degrees Fahrenheit does not mean no temperature, so the scale cannot be ratio. C is wrong because nominal data has no numeric meaning beyond grouping. Temperature numbers have full quantitative meaning and can be added or averaged. D is wrong because while temperatures can be ranked, the data type is defined by more than just rank. Equal intervals and arithmetic operations make the data interval rather than ordinal. Interval data is the third level in the measurement hierarchy. It inherits every property of ordinal data and adds one critical feature: equal numeric distance between adjacent values. 4 key properties define interval data. Values are equally spaced, so means and standard deviations are valid, but the 0 point is arbitrary. It does not represent a true absence of the quantity, and that makes ratio statements meaningless. Temperature in Fahrenheit is the classic example. 0 degrees Fahrenheit is an arbitrary reference, the freezing point of a saltwater brine. not the absence of heat. Kelvin, by contrast, anchors at absolute zero where molecular motion ceases, making it ratio data. Common interval examples include Fahrenheit, Celsius, calendar years, and IQ scores all have arbitrary zeros. Ratio data like length of stay in hours. Kelvin, weight, and height share a true zero that permits statements like one value is twice another. The exam test is always the meaning of zero. If zero on the scale still represents some amount of the quantity, as with Fahrenheit, the variable is interval. Only when zero means a genuine absence does the scale rise to ratio level. Question 4. A hospital reports its catheter-associated urinary tract infection rate per 1,000 catheter days. Which data classification applies to this reported rate? Your options are A. Ordinal data because the rate can be ranked among hospitals. B. Nominal data because each rate is a unique value. C. Interval data because the rate values are evenly spaced. D. Ratio data because the rate has a true 0 point. What's your answer? Commit to one before I continue. The correct answer is D. Ratio data because the rate has a true 0 point. D is correct because an infection rate of 0 means no infections occurred during the measurement period, which is a real and meaningful absence of the quantity. That true 0 is the defining feature of ratio data and allows statements like one hospital has twice the rate of another. A is wrong because although rates can be ranked, ordinal data is limited to relative ordering without true mathematical operations on the values themselves. Rates support full arithmetic, making them ratio. B is wrong because nominal data uses labels without numeric meaning. Infection rates are quantitative numbers, not category labels. C is wrong because interval data lacks a true 0. The infection rate scale anchors at 0 infections, which gives it the additional ratio property. Ratio data sits at the top of Stevens' 4-level measurement hierarchy. It inherits everything from interval data, equal spacing and full arithmetic, and adds one critical feature, a true 0 that means the genuine absence of the quantity. Ratio scales have equal intervals and support arithmetic just like interval scales. The defining addition is a true 0 anchor, which makes proportional statements valid. You can say one unit has twice the infection rate of another, something interval data simply cannot support. Common healthcare examples include SARTI rates, length of stay, blood pressure, and patient age. In every case, a value of 0 represents a real, meaningful absence. 0 infections, 0 days admitted, 0 years of age. Testing a scale is straightforward. Identify what 0 means on that scale and ask whether it represents none of the quantity. A hospital with 0 infections had no infections. A patient with 0 days of stay was never admitted. If 0 equals none, the scale is ratio. The classic exam mistake is labeling a ratio scale as interval because both look numeric and support the same statistical test. The correct check is always the meaning of 0. Proportional language, rates drop by half, 1 unit has twice the rate, signals ratio data every time. Question 5. A healthcare leader plans to calculate the average length of stay in days for surgical patients and compare it against the previous quarter. Which data classification supports this analysis with the most flexibility? Your options are A. Nominal data, which counts the frequency of each stay length. B. Ordinal data, which ranks stays from shortest to longest. C. Ratio data, which permits arithmetic and proportional comparisons. D. Interval data, which allows averages but no proportional claims. Pick one. Trust your gut. Here's your chance to test yourself. The correct answer is C. Ratio data, which permits arithmetic and proportional comparisons. C is correct because length of stay measured in days has a true zero, equal intervals, and supports every mathematical operation a leader would need. That makes it ratio data and the most flexible classification for averaging and comparing quarterly results. Statements like patients now stay half as long are valid. A is wrong because nominal data only supports counting frequencies of categories. Averaging stay length requires quantitative operations that nominal data does not permit. B is wrong because ordinal data preserves rank, but not the precise mathematical distance between values. Averages calculated on rank alone are statistically unreliable. D is wrong because interval data would allow computing an average but would not support saying one period is proportionally smaller than another because there is no true zero anchor. Ratio data sits at the top of the measurement hierarchy, and that position gives analysts the widest possible set of tools. Understanding why ratio is so powerful starts with seeing what each level of measurement actually adds. There are 4 levels in the measurement hierarchy. Nominal supports only counts. Ordinal adds rank-based comparison. Interval adds means and standard deviations. Ratio adds proportional statements, like percentage change and doubling, making every prior tool available plus new ones. Length of stay in days is one of the clearest ratio examples in healthcare. 0 days is a genuine state. Intervals are equal, and proportional statements are valid. A CFO can defensively say cardiothoracic stays dropped by 12% quarter over quarter. On exam day, watch for signal words like percentage changed, proportional comparison, doubling or halving, and full parametric analyses. Whenever the question describes those operations, ratio is almost certainly the correct answer. The key trap is assuming ratio is always better. Cancer stage is genuinely ordinal and cannot be forced into ratio interpretations. The skill is matching the measurement scale to the underlying construct, so every statistical statement you make is defensible. Question 6. A research team studies whether a new shift handoff protocol reduces medication errors on a hospital unit. Half the unit uses the new protocol, the other half uses the traditional approach. Which factor is the independent variable in this study? Your options are A. The type of handoff protocol assigned to each group. B. The number of medication errors recorded each week. C. The age of the nurses delivering each shift handoff. D. The acuity level of the patients on the unit. Which would you go with? Lock it in before the reveal. The correct answer is A. The type of handoff protocol assigned to each group. A is correct because the independent variable is the factor the researchers deliberately manipulate to observe its effect. Here, the researchers assign one group to the new protocol and the other to the traditional approach. That deliberate choice of protocol is what they control, so it is independent. B is wrong because medication errors are the outcome the researchers are measuring. That makes errors the dependent variable, not the independent one. C is wrong because nurse age is not being manipulated by the researchers, and unless it is being studied as the experimental factor, it is not the independent variable. D is wrong because patient acuity could potentially confound the results if not controlled, but the researchers are not deliberately varying acuity. It is therefore not the independent variable in this design. In any study, the independent variable is the factor the researcher deliberately manipulates or selects to observe its effect on something else. It sits on the input side of the research question, the cause the researcher is testing. Whether the study is experimental or observational, the researcher either assigns a treatment, sorts participants into groups by a characteristic, or tracks a defined exposure. That deliberate choice is what makes the variable independent. Think of it as 2 sides of the research question. The independent variable is what the researcher varies, like assigning a new handoff protocol to one unit. The dependent variable is what gets measured in response, like medication errors. The common exam trap is confusing a confounding variable with an independent variable. If the researcher sorted on it, like protocol assigned or diagnosis, it is independent. If a difference just appears, like age or patient acuity, it is a confounder, not the independent variable. Every time you see a research stem, ask, which factor did the researcher choose to manipulate or sort on? That factor is the independent variable. The factor that responds and gets measured is always dependent. Question 7. A clinical analyst evaluates whether a new sepsis screening tool changes patient mortality on a medical surgical floor. Which factor in this study is the dependent variable? Your options are A. The training schedule offered to the screening nurses. B. The version of the sepsis screening tool used. C. The shift length of the staff conducting the screen. D. The mortality rate observed in screened patients. Don't overthink it. Which one feels right? The correct answer is D. The mortality rate observed in screened patients. D is correct because the dependent variable is the measurable outcome that responds to changes in the independent variable. Mortality is the result the analyst tracks to determine whether the screening tool makes a difference. That outcome dependence is the defining feature of a dependent variable. A is wrong because the training schedule could influence how well the tool is used, but is a procedural choice, not the outcome the analyst is measuring. B is wrong because the screening tool itself is the input the analyst is manipulating, which makes it the independent variable rather than the dependent one. C is wrong because shift length is a contextual factor that could confound results if it differs between groups, but it is not the outcome under study. The dependent variable is the outcome a researcher measures to see whether changes in the independent variable produced a real effect. It is the response side of every study question, the consequence, not the cause. 4 features define the dependent variable. It is measured rather than assigned. It responds to the independent variable. It is the result the study is built to report. And its measurement scale determines which statistical test applies. Picture the independent variable on the left, the factor the researcher assigns or controls, with an arrow pointing to the dependent variable on the right, the outcome being measured. The entire study is built to test whether that arrow represents a real relationship. On exam stems, watch for signal words, outcome, response, endpoint, measured or recorded, effect, and phrases like the change in or the level of. These almost always point to the dependent variable, the thing the researcher is tracking to see whether the intervention worked. When in doubt, ask 2 questions. What did the researcher control or assign? And what did they measure in response? The first is independent, the second is dependent. That clean separation is what holds the logic of any study together. Question 8. A health system finds that patients who attend a new diabetes education program have lower hemoglobin A1C readings than patients who decline the program. A researcher worries the result might be driven by something else entirely. Which variable type best describes the unmeasured factor that could distort the apparent effect? Your options are A dependent variable that shifts as the program scales. B, a confounding variable that hides the true relationship. C, a dichotomous variable that splits patients into 2 groups. D, a continuous variable that varies smoothly with treatment. Got a guess? Lock it in. The correct answer is B, a confounding variable that hides the true relationship. B is correct because a confounding variable is an outside factor that affects both the independent and dependent variables and can make the relationship between them appear stronger or weaker than it really is. Motivation, baseline health literacy, or socioeconomic stability could all be confounders here. Ignoring them risks crediting the program for outcomes it did not cause. A is wrong because a dependent variable is the outcome being measured, in this case A1C. The researcher is not worried about A1C itself, but about an external factor influencing it. C is wrong because a dichotomous variable simply splits a population into two categories. While participation in the program is dichotomous, that descriptor does not address the concern about hidden distortion. D is wrong because a continuous variable changes along a numeric scale. That descriptor identifies the form of data but does not describe a hidden third factor distorting the effect. A confounding variable is a third factor that simultaneously influences both the independent variable and the dependent variable, creating a distorted or entirely false appearance of a relationship between them. Understanding how confounders work is central to interpreting research correctly. A variable only qualifies as a confounder if it meets three conditions. It must be linked to the independent variable, it must independently affect the dependent variable, and critically, it must not sit on the causal pathway between them. Age is a classic example in medical research because older patients differ across dozens of factors that can drive outcomes. The key distinction to remember is between a confounder and a mediator. A mediator sits directly on the causal pathway, and think inflammation, linking a treatment to its outcome. A confounder sits off to the side, distorting what the relationship looks like without being part of how it actually works. Confounders can distort analysis in multiple directions. They can hide a true effect, inflate a weak one, manufacture a relationship where none exists, or cause researchers to credit the wrong cause. This is why controlling for confounding through randomization, matching, stratification, or multivariate regression is a foundational task in research design. Whenever a research stem describes an unmeasured factor, a hidden influence, or an alternative explanation for a result, that is a signal word for confounding. Apply the three-condition test to confirm them. And remember, confounding is an analytic flaw to correct, not a real subgroup phenomenon to report. Question 9. A nurse manager records the length of each post-operative stay in hours for cardiac surgery patients. Which best describes this variable? Your options are A dichotomous variable with two possible states, B, a categorical variable made up of name groups, C, a continuous variable with meaningful differences across values, D, an ordinal variable that ranks stays into tiers. Which one is it? Pause the video if you need more time. The correct answer is C, a continuous variable with meaningful differences across values. C is correct because a continuous variable can take any value within a numeric range, and the difference between any two values has consistent meaning. Hours of stay can include fractional values and supports arithmetic, such as averages and standard deviations. That mathematical richness is what makes it continuous. A is wrong because dichotomous variables hold exactly two values, like yes or no. Stay length spans an entire numeric range, far beyond two categories. B is wrong because categorical variables use named labels rather than quantities. Hours are numbers, not category names. D is wrong because ordinal variables enforce ranking without guaranteeing equal numeric distances. Length of stay is fully quantitative, so it surpasses ordinal characteristics. A continuous variable can take any value within a numeric range, and the difference between two values carries consistent, meaningful quantity. This is the foundation that makes parametric statistics possible. The defining feature of a continuous variable is the smoothness of its underlying scale. Length of stay can be 37.5 hours. Hemoglobin A1C is reported to the 0.1%, and age can be measured to the day. A discrete variable, by contrast, jumps only in whole number increments. That granularity is what allows full arithmetic. Continuous variables support means, standard deviations, confidence intervals, and the full suite of parametric tests, operations that require the spacing between values to be consistent and meaningful. Watch for two common exam traps. Whole number counts, like number of children or prior admissions, are technically discrete, not continuous. And ordinal scales may use numbers, but unequal spacing between levels rules out arithmetic, so they are not continuous either. The quickest check on exam day: ask whether the variable supports addition, subtraction, and averages across a smooth range. If yes, it is continuous. Signal words include measured, recorded with decimals, weight, time, length, and blood pressure. Question 10. A clinical registry tracks whether each admitted patient has a documented advance directive. The column accepts only yes or no for each entry. Which best describes this variable? Your options are A dichotomous variable with exactly two possible states. B, a continuous variable measured on a numeric scale. C, an ordinal variable that ranks documentation depth. D, a ratio variable that supports proportional comparison. Take a second. Which answer would you pick? The correct answer is A, a dichotomous variable with exactly two possible states. A is correct because a dichotomous variable allows only two mutually exclusive values. The advanced directive column holds either yes or no for every patient, which fits the definition exactly. Many clinical and demographic factors take this binary form. B is wrong because continuous variables can hold any value within a numeric range. Yes and no are not points on a numeric scale. C is wrong because ordinal variables imply a meaningful order. Yes and no can be coded but do not represent a ranked progression. D is wrong because ratio variables require numeric measurement with a true zero. A yes or no value cannot be expressed as a quantity, so ratio does not apply. A dichotomous variable is one that takes exactly two mutually exclusive values, and every observation must fall into one or the other. This binary structure is one of the most common data types in healthcare analytics. The defining features are straightforward. There are precisely two states. Every observation is assigned to one, and no middle ground exists. Dichotomous variables are a special case of categorical data, restricted to exactly two values. Unlike categorical variables, which can have many, in clinical and administrative data, binary facts appear constantly. A test is positive or negative. A patient is readmitted or not. An advance directive is present or absent. These yes or no fields are the natural home of dichotomous classification. Each observation is coded as a 1 or a 0, a yes or a no. That simple coding lets the variable participate in regression models, contingency tables, and proportions analysis. From the proportion in one state, analysts compute rates, odds, and risks. Because the structure is so clean, specialized tools are built around it. The chi-square test, logistic regression, and proportions analysis all assume binary or categorical outcomes, making dichotomous variables the direct input these methods are designed for. Question 11. A hospital nurse manager wants to test whether a new hand hygiene protocol changes the average number of sanitizer dispensees per shift on a single unit. The manager collects 25 shifts under each protocol. Which statistical test best fits this situation? Your options are A, chi-square, because the data tracks adherence behaviors across two settings. B, ANOVA, because two protocols are being compared in one run. C, z-test, because the sample size sits well above 30. D, two-sample t-test, because two independent group means are compared with small samples. Before I reveal it, which one do you think is right? The correct answer is D, two-sample t-test, because two independent group means are compared with small samples. D is correct because a two-sample t-test compares the means of two independent groups. When the sample size is modest, typically below 30 per group. The manager has 25 shifts in each arm, an independent grouping, and a single mean to compare. That matches the t-test profile exactly. A is wrong because chi-square examines association between categorical variables. Dispense counts are continuous measurements, not categories. B is wrong because ANOVA is designed for 3 or more groups. With only 2 protocols, a t-test is the simpler and more appropriate choice. C is wrong because the z-test requires either a large sample size or known population variance. 25 shifts per group is too small to justify z-test assumptions. The two-sample t-test is one of the most widely used tools in applied statistics. It was invented by William Seeley Gosse, writing as student, while comparing small barley samples at the Guinness Brewery in 1908. His need for a small sample comparison tool gave us a method that healthcare analysts still rely on every day. Reach for the two-sample t-test when you have 2 independent groups, a continuous numeric outcome, and modest sample sizes, usually fewer than 30 per group. It assumes roughly normal distributions and equal variances, and it estimates the unknown population variance directly from your sample data. The test statistic is simply the difference between the 2 group means divided by the pooled standard error. When the difference is large relative to within-group variability, the t-statistic grows and the p-value shrinks. A p-value below 0.05 tells you the observed difference would be unlikely if both groups were drawn from the same population. Know when not to use the two-sample t-test. If the same subjects are measured twice, use the paired t-test. If you have 3 or more groups, use ANOVA. Running multiple t-tests inflates false positives. And if normality or equal variance assumptions are clearly violated, the Mann-Whitney U is the non-parametric alternative. On exam day, look for stems describing 2 independent groups compared on a numeric outcome with modest sample sizes. That pattern almost always points to the two-sample TD test. Keep the contrast sharp. Paired data needs the paired TI test. 3 or more groups need ANOVA. Question 12. A clinical researcher wants to compare the average wait times across 4 emergency department triage workflows. Sample variance and distribution appear roughly similar. Which statistical test best supports this analysis? Your options are A. Paired t-test, designed for matched observations. B. Analysis of variance, designed for comparing 3 or more group means. C. Pearson correlation, designed for relationships between 2 continuous variables. D. Chi-square, designed for relationships among categorical variables. What's your answer? Commit to one before I continue. The correct answer is B. Analysis of variance, designed for comparing 3 or more group means. B is correct because analysis of variance, commonly known as ANOVA, compares the means of 3 or more independent groups in a single statistical test. The 4 workflows form 4 independent groups with continuous wait time as the outcome. Roughly equal variance and normality satisfy the test assumptions. A is wrong because a paired t-test handles 2 related observations on the same unit, such as before and after measurements. The 4 workflows are independent of each other, so pairing does not apply. C is wrong because Pearson correlation describes how 2 continuous variables move together. The researcher is comparing groups, not relating one variable to another. D is wrong because chi-square handles categorical associations such as workflow choice against patient acceptance status. With continuous wait times, chi-square would lose statistical power. ANOVA extends the logic of the t-test to situations with 3 or more independent groups. Rather than asking whether 2 means differ, it asks whether all group means are equal, or whether at least one stands apart. Because ANOVA is parametric, it carries 3 assumptions: normality within groups, roughly equal variances across groups, and independent observations. When these hold, ANOVA controls the false positive rate that would balloon if you ran many separate t-tests. The core mechanism is partitioning total variance into two parts: variance between groups and variance within groups. Their ratio is the F statistic. A large F means group differences are big relative to background noise, signaling that at least one mean truly differs. Choosing the right test hinges on group count and outcome type. ANOVA handles continuous outcomes across 3 or more groups. The two-sample t-test covers 2 groups. Chi-square addresses categorical outcome. When equal variance assumptions break down, Kruskal-Wallis is the non-parametric fallback. On exam day, count the groups first. 3 or more groups with a continuous outcome, comparing 4 triage workflows or 3 treatment protocols, points directly to ANOVA. If a significant F emerges, post hoc tests like Tukey or Bonferroni then identify which specific pairs differ. Question 13. Before running an ANOVA, a quality analyst wants to confirm that 2 patient satisfaction populations have equal variance. Which statistical test directly compares the variances of 2 populations? Your options are A. F test, which uses the ratio of variances to test equality. B. Paired t-test, which compares related observation means. C. Chi-square, which compares observed and expected frequencies. D. Linear regression, which models a predictor against an outcome. Pick one. Trust your gut. Here's your chance to test yourself. The correct answer is A. F-test, which uses the ratio of variances to test equality. A is correct because the F-test forms a ratio between 2 sample variances and asks whether that ratio is statistically close to 1. When the ratio is near 1, the variances are likely equal. This is precisely the assumption check that ANOVA relies on before testing means. B is wrong because A paired t-test focuses on differences between related means, not on the spread of values within each group. C is wrong because chi-square evaluates how observed counts deviate from expected counts in categorical data. It does not address variance equality in continuous data. D is wrong because linear regression models the relationship between predictor and outcome, but is not designed to compare variances between 2 populations. The F-test is a parametric procedure designed to determine whether 2 populations share the same spread. It relies on the F distribution, named in honor of Ronald Fisher, and shows up both as a standalone test and as the core statistic inside ANOVA. The test statistic is simply the ratio of 2 sample variances, the larger divided by the smaller. When that ratio is close to 1, the variances are likely equal. When it departs sharply from 1, the test rejects the null hypothesis of equal variance. A common exam trap is blurring these 3 tests. The F-test compares variances. The t-test compares 2 means. ANOVA compares means across more than 2 groups, but uses an F ratio internally. Each answers a different research question. On exam day, look for stems that describe an analyst verifying whether 2 populations have similar spreads, or performing a preliminary check before another parametric test. Those phrases are pointing directly at the F-test, not the t-test and not chi-square. The cleanest way to avoid misselection is to ask what the research question actually concerns. The F-test answers questions about variability. Choosing the right tool starts with identifying the right question. Question 14. A network of 200 ambulatory clinics tracks an average daily appointment count, with known population variance from years of historical data. Which task fits when comparing this network mean to a known benchmark? Your options are A. Mann-Whitney U-test, used when the underlying distribution is unknown. B. Paired t-test, used when small samples track the same units twice. C. Z-test, used when the sample is large and population variance is known. D. D. Pearson correlation used when two continuous variables relate. Which would you go with? Lock it in before the reveal. The correct answer is C. Z-test used when the sample is large and population variance is known. C is correct because the Z-test applies when the sample size is large, typically above 30, and the population variance is already known. 200 clinics is well above the threshold, and the network has accumulated population variance from history. Those two conditions together signal a Z-test. A is wrong because Mann-Whitney U fits when ranks are needed and distribution assumptions are violated. The clinic data is continuous and ample, so a Z-test is more powerful. B is wrong because A paired t-test fits modest samples with related pre- and post-observations. The scenario is a single mean against a benchmark, not paired measurements. D is wrong because Pearson correlation describes the strength of a relationship between two variables. The scenario is testing one mean, not measuring a relationship. The Z-test is a parametric hypothesis test used when you have a large sample and already know the population variance from prior data. It tells you whether a sample mean or proportion differs significantly from a known benchmark. 3 conditions must hold before you can reach for the Z-test. Your sample size should be above 30. The population variance must already be known from historical data, and the sampling distribution of the mean must be approximately normal, which the central limit theorem guarantees at large sample sizes. The Z statistic is the difference between the sample mean and the population mean divided by the standard error. The resulting value is compared against the standard normal distribution. A Z value beyond plus or minus 1.96 marks statistical significance at the 5% level in a two-tailed test. The key contrast is with the t-test. Use the Z-test when sample size is large and variance is known. Switch to the t-test when sample size is small or variance must be estimated from the sample itself. Applying the Z-test when these conditions fail is the classic exam trap. On exam day, look for large data sets compared against historical benchmarks with a known population variance. That combination is the signature of the Z-test and points you to the right choice every time. Question 15. A bariatric clinic measures body mass index in the same patient cohort before and after a year-long behavior change program. The clinic wants to test whether the average BMI changed. Which statistical test fits the design? Your options are A. 2-sample t-test designed for 2 independent groups. B. Paired t-test designed for related observations on the same units. C. ANOVA designed for 3 or more independent groups. D. Chi-square designed for categorical association. Don't overthink it. Which one feels right? The correct answer is B. Paired t-test designed for related observations on the same units. B is correct because a paired RT test compares 2 means when each pair of observations is drawn from the same unit. Every patient contributes a before value and an after value, so the data is matched at the individual level. That match structure is exactly what the paired t-test handles. A is wrong because a 2-sample t-test treats the 2 measurements as if they came from independent groups. The same patients appearing twice violates the independence assumption. C is wrong because ANOVA fits 3 or more groups, not 2 paired sets. With only 2 time points and matched observations, ANOVA would discard valuable pairing information. D is wrong because chi-square fits categorical association, not continuous outcomes measured before and after on the same patients. The paired t-test is built around a simple but powerful idea. When 2 measurements come from the same subject or matched pair, that link contains information you should not throw away. The defining structure is one-to-one correspondence. The three most common setups are before and after measurements, within-body comparisons, and matched case-controlled designs where cases and controls are paired on key characteristics. For each pair, the analyst computes a single difference score. The mean of those differences divided by the standard error of the mean gives the paired t-statistic, which follows a t-distribution with degrees of freedom equal to the number of pairs minus 1. By focusing on within-pair differences, the test strips away the baseline variability that exists between different subjects. That reduction in noise is why paired designs yield greater statistical power than independent sample comparisons on the same data. The classic mistake is treating paired data as independent, which discards the pairing structure and produces a weaker, potentially misleading result. The reverse error, forcing a pairing onto truly independent groups, is equally wrong. The design of the data, not convenience, dictates which tests to use. Question 16. A public health analyst wants to test whether vaccination status is associated with reported flu-like symptoms during a regional outbreak. Both variables are categorical. Which statistical test best fits? Your options are A. Pearson correlation, which fits continuous variable pairs. B. ANOVA, which compares means across 3 or more groups. C. Linear regression, which models continuous outcomes. D. Chi-square, which tests association between categorical variables. Got a guess? Lock it in. The correct answer is D. Chi-square, which tests association between categorical variables. D is correct because chi-square is the standard test for assessing whether two categorical variables are associated. Vaccination status is yes or no, and symptom reporting is yes or no. The test compares observed counts in each cell of the contingency table to the counts expected under independence. A is wrong because Pearson correlation operates on continuous numeric pairs. Categorical labels do not produce the kind of numeric variation Pearson needs. B is wrong because ANOVA compares group means on a continuous outcome. With both variables categorical, there is no continuous outcome to average. C is wrong because linear regression predicts a continuous outcome from one or more predictors. Categorical outcomes shift the analysis toward logistic methods or chi-square. The chi-square test is a non-parametric method for evaluating whether observed counts in categorical data differ from what we'd expect under a null hypothesis. It doesn't require continuous or normally distributed data. It works entirely on counts falling into discrete categories. Chi-square comes in 2 main forms. The goodness of fit test asks whether observed frequencies match a hypothesized distribution. The test of independence asks whether two categorical variables are associated in a contingency table. Both rely on the same underlying mathematics. The chi-square statistic is calculated from a contingency table. Each cell's expected frequency equals its row total times its column total divided by the grand total. The statistic sums the squared difference between observed and expected counts divided by expected. A large value signals that the variables are likely associated. Chi-square compares counts, not means. That's what separates it from t-test and ANOVA. When the question involves two categorical variables, chi-square fits. When multiple categorical predictors are involved, logistic regression is the right tool. The key exam warning: chi-square requires every expected cell count to be at least 5. If expected counts are too small, often from grouping continuous data into broad categories, the approximation breaks down. In those cases, Fisher's exact test is the reliable alternative. Question 17. A researcher needs to compare median patient-reported pain scores between 2 clinics. The pain scores are ordinal and not normally distributed, so the t-test assumptions cannot be met. Which test fits? Your options are A. Mann-Whitney U test, designed for ordinal or non-normal data between two groups. B. Two-sample t-test, the standard test for two-group continuous comparisons. C. ANOVA, designed for three or more independent groups. D. Z-test, designed for known population variance and large samples. Which one is it? Pause the video if you need more time. The correct answer is A. Mann-Whitney U test, designed for ordinal or non-normal data between two groups. A is correct because the Mann-Whitney U test is the non-parametric alternative to a two-sample t-test. It compares two independent groups when the data is ordinal or when the normality assumption fails. Pain scores meet both conditions, so Mann-Whitney is the natural choice. B is wrong because a two-sample TT test assumes the data is continuous and roughly normal. Ordinal scores that violate normality undermine its validity. C is wrong because ANOVA compares means across three or more groups and shares the same parametric assumptions as the TR test. The scenario has two groups, not three. D is wrong because a Z-test applies when the sample is large and population variance is known. Neither condition is stated, and the deeper concern about ordinal non-normal data still rules out Z. The Mann-Whitney U test is the non-parametric alternative to the two-sample t-test. Rather than comparing means, it compares the ranks of observations across two independent groups, making it valid when normality cannot be assumed. Use Mann-Whitney when your data are ordinal, or when continuous data violate the normality assumption through skew or outliers. Both situations make the TE test invalid, and Mann-Whitney handles both. The core mechanism converts raw values into ranks. All observations from both groups are pooled and ranked from lowest to highest. The sum of ranks in each group is then compared. If one group consistently holds higher ranks, it tends to have higher values, and the U statistic captures exactly that difference. The key contrast is straightforward. The t-test compares means and requires normality. Mann-Whitney compares ranks and requires neither. The t-test is more powerful when its assumptions hold, but Mann-Whitney remains valid across a wider range of data shapes. On the exam, watch for ordinal data, non-normal distributions, or ranked observations with two independent groups. Those are all pointing at Mann-Whitney. The phrase non-parametric alternative to the TT test is a near giveaway. Question 18. A healthcare data analyst plots length of stay against total billed charges across 1,000 discharges and finds a Pearson correlation coefficient close to +1. Which best interprets this result? Your options are A. A weak inverse relationship that reverses direction over time. B. A moderate negative relationship suggesting one variable drives the other down. C. A strong positive relationship in which the two variables tend to move together. D. A complete absence of association between the two variables. Take a second. Which answer would you pick? The correct answer is C. A strong positive relationship in which the two variables tend to move together. C is correct because Pearson correlation ranges from -1 to +1. A value near +1 indicates a strong direct relationship. As one variable rises, the other tends to rise as well in near linear fashion. Length of stay and bill charges climbing together is exactly what would be expected. A is wrong because a weak inverse relationship would produce a small negative coefficient, not a strong positive one. B is wrong because a moderate negative relationship would yield a value between -0.3 and -0.7. A value close to +1 is the opposite direction. D is wrong because 0 indicates no linear association. A value near +1 is at the opposite extreme from 0. Pearson's correlation coefficient measures the strength and direction of a linear relationship between two continuous variables. The result, written as R, always falls between -1 and +1. A value near +1 means the variables rise together in a tight pattern. Near -1 means an equally tight pattern moving in opposite directions. Near 0 means no linear relationship exists, though nonlinear patterns can still be present. Visualizing R on a scatterplot makes the concept concrete. A tight upward cloud signals a strong positive correlation. A tight downward cloud signals a strong negative correlation. And a diffuse random cloud signals no linear association at all. Pearson R assumes both variables are continuous and approximately normally distributed, because the formula standardizes by dividing by the product of the two standard deviations. The coefficient is unit-free. A correlation of 0.8 means the same whether variables are in dollars and days or pounds and degrees. The critical exam trap is interpreting correlation as causation. A strong R between length of stay and billed charges does not mean one causes the other. Patient complexity may drive both. Correlation describes how two variables move together. Only controlled study designs can establish why. Question 19. A finance team in a health system wants to predict next year's outpatient revenue based on a single predictor. The number of scheduled visits? Which statistical method fits? Your options are A. Pearson correlation, which measures relationship strength but not prediction. B. Simple linear regression, which uses one predictor to forecast one outcome. C. Chi-square test, which evaluates categorical associations. D. ANOVA, which compares average outcomes across multiple groups. Before I reveal it, which one do you think is right? The correct answer is B. Simple linear regression, which uses one predictor to forecast one outcome. B is correct because simple linear regression models the relationship between one independent variable and one continuous outcome, producing a line that can predict future outcome values from observed predictor values. With visits as the only predictor and revenue as the outcome, simple linear regression is the textbook tool. A is wrong because Pearson correlation describes how strongly two variables move together, but does not produce a predictive equation. C is wrong because chi-square evaluates association between categorical variables. Visit count and revenue are continuous, so chi-square would discard most of the information. D is wrong because ANOVA compares means among three or more groups, not the prediction of a continuous outcome from a continuous predictor. Simple linear regression fits a straight line through data to predict a single continuous outcome from a single predictor variable. It's one of the oldest statistical tools, rooted in Francis Galton's work on hereditary patterns in the late 1800s. The regression line is defined by two values: the intercept, where the line crosses the outcome axis when the predictor is 0, and the slope, which tells us how much the outcome changes for each 1 unit increase in the predictor. Together they form the equation y equals a plus b times x. Simple linear regression is parametric, meaning it rests on 4 core assumptions: a linear relationship, normally distributed residuals, constant variance, and independent observations. When these hold, the method finds the line that minimizes the sum of squared residuals, the best fitting line by that criterion. 2 traps appear frequently on exams. First, a regression line does not prove causation. A relationship between visits and revenue may be driven by unmeasured variables. Second, prediction should not be extrapolated far beyond the observed data range, where the linear pattern may no longer hold. The clearest contrast is with multiple regression, which handles several predictors jointly, and with Pearson correlation, which measures relationship strength but produces no predictive equation. Simple linear regression is the foundation everything else is built on. Question 20. An analyst predicting hospital readmission rates wants to use age, diabetes status, length of prior stay, and number of medications all at once as predictors. Which technique is appropriate? Your options are A. Simple linear regression, which uses one predictor only. B. Pearson correlation, which describes pairwise relationships. C. Chi-square, which deals with categorical relationships only. D. Multiple linear regression, which models several predictors against one outcome. What's your answer? Commit to one before I continue. The correct answer is D. Multiple linear regression, which models several predictors against one outcome. D is correct because multiple linear regression extends simple linear regression by accepting two or more predictors simultaneously, producing a coefficient for each one while controlling for the others. Age, diabetes status, prior stay length, and medication count all contribute to a single readmission rate prediction. Multiple regression handles them in one model. A is wrong because simple linear regression is limited to one predictor and cannot evaluate the joint influence of several variables. B is wrong because Pearson correlation describes pairs of variables one at a time and is not designed for combined predictive modeling. C is wrong because Chi-square handles categorical associations. With both continuous and categorical predictors and a continuous outcome, Waxeeds ends odd. Chi-square is not the appropriate framework. Multiple linear regression extends the simple regression framework by allowing two or more predictors to jointly explain a continuous outcome in a single model. The model produces one equation. The outcome equals an intercept plus the sum of each predictor multiplied by its own coefficient. Each coefficient tells you how much the outcome changes for a 1 unit increase in that predictor, while all other predictors are held constant. That isolation is the core advantage. Multiple regression inherits the standard assumptions, linearity, approximately normal residuals with constant variance, and independent observations. It adds two more concerns. Predictors must not be too highly correlated with each other, a problem called multicollinearity, and the analyst must carefully choose which predictors belong in the model. A common exam trap is assuming that adding more predictors always improves the model. Each added predictor consumes a degree of freedom and risks overfitting. Measures like adjusted R-squared and cross-validation help balance fit against complexity. The cleanest exam signal is the number and type of predictors alongside the outcome scale. One predictor points to simple linear regression. Multiple predictors with a continuous outcome call for multiple linear regression. A binary outcome with multiple predictors calls for logistic regression. Question 21. A regional public health team surveys a sample of 7,000 adults on a single day to learn how many currently smoke cigarettes. The team reports findings as the percentage of smokers at that moment. Which study design fits this approach? Your options are A. Time series analysis with measurements gathered at regular intervals. B. Longitudinal cohort study with follow-up across years. C. Cross-sectional study that captures data at a single point in time. D. Randomized control trial that assigns participants to interventions. Pick one. Trust your gut. Here's your chance to test yourself. The correct answer is C. Cross-sectional study that captures data at a single point in time. C is correct because a cross-sectional study collects information from a population at one specific point in time, producing a snapshot of prevalence. Surveying 7,000 adults on a single day to estimate the current smoking rate matches the definition precisely. Cross-sectional designs are common for prevalence reporting. A is wrong because time series analysis tracks the same metric at predetermined intervals across a span of time. A single survey day does not produce a time series. B is wrong because a longitudinal cohort follows participants over months or years to detect change. The survey ends after 1 day, so it cannot follow trajectories. D is wrong because randomized controlled trials assign participants to interventions and observe outcomes. The survey does not assign any intervention. A cross-sectional study captures a single snapshot of a population at one moment in time. It's the design behind prevalence surveys, opinion polls, and one-time descriptive reports. Understanding what this design can and cannot tell us is essential for interpreting research findings correctly. Cross-sectional designs are popular for 3 reasons. They are fast and inexpensive, they measure current prevalence directly, and they require no follow-up period. A health system estimating hypertension rates or vaccination coverage in a county can get answers quickly without committing to years of data collection. The key mechanism is simultaneous measurement. Exposure and outcome are captured in each participant at the same moment. This tells the researcher whether the two are associated in the population, but because there is no time ordering, it cannot establish which came first or whether one caused the other. This is the critical exam trap. Never assume an association found in a cross-sectional study is causal. 4 limitations explain why the design establishes no causation, imposes no time order, leaves reverse causation possible, and leaves confounding unresolved. The cleanest way to identify a cross-sectional study is this. If each participant contributes one set of measurements on one occasion with no follow-up, the study is cross-sectional. Signal words on exam stems include snapshot, single point in time, prevalence, and current rate. Question 20. A health services researcher follows the same cohort of 2,000 newly diagnosed diabetic patients for 10 years to track cardiovascular outcomes. Which study design fits this approach? Your options are a longitudinal study that follows the same participants across time. B. Cross-sectional study that captures a single point in time. C. Case study that explores one patient in detail. D. Meta-analysis that synthesizes existing trials. Which would you go with? Lock it in before the reveal. The correct answer is A. Longitudinal study that follows the same participants across time. A is correct because a longitudinal study follows a defined set of participants over an extended period, gathering data at multiple points so the researcher can observe how outcomes evolve. The 10-year follow-up of 2,000 patients is a textbook example. The repeated measures support causal reasoning about exposure and outcome. B is wrong because cross-sectional studies capture one moment, not a trajectory. The 10-year timeline rules out cross-sectional. C is wrong because a case study examines a single person or small group in depth. 2,000 participants and a decade of follow-up exceed the case study format. D is wrong because a meta-analysis combines results from many already completed studies. The researcher in the scenario is collecting new data, not combining existing trials. A longitudinal study follows the same participants over time, collecting repeated measurements to reveal how outcomes evolve. This design is central to natural history research, prognostic modeling, and identifying risk factors. The essential contrast is this. Cross-sectional studies measure each person once, capturing a single snapshot. Longitudinal studies measure each person multiple times, tracking change from a baseline through follow-up visits spanning months or even decades. By following the same individuals forward in time, these designs reveal incidence, the sequence of exposure before outcome, and individual trajectories, providing the temporal structure needed to support causal reasoning. A key exam trap is confusing longitudinal with time series designs. Time series tracks aggregate population metrics, like monthly ED visits, while longitudinal designs track individual people. When a STEM describes years of follow-up on a defined cohort, that is your signal for a longitudinal design. The power of longitudinal designs comes from linking repeated observations on the same subjects, but that power carries a price. Tracking participants over years demands investment in retention and follow-up infrastructure that a cross-sectional study completed in a week simply does not require. Question 23. A health system tracks emergency department visit volume on the first Monday of every month over 5 years to look for seasonal and structural patterns. Which study design best describes this approach? Your options are A. Cross-sectional study with a single point in time. B. Time series analysis with regular intervals across a longer window. C. Meta-analysis of multiple ED operation studies. D. Randomized controlled trial of triage interventions. Don't overthink it. Which one feels right? The correct answer is B. Time series analysis with regular intervals across a longer window. B is correct because time series analysis collects sequential data at predetermined intervals, so trends, seasonality, and structural shifts can be detected. Recording ED volume on the first Monday of every month for 5 years produces a regular interval series. It is a defining example of the design. A is wrong because a cross-sectional study collects data at one point in time. Repeated monthly readings across 5 years extend well beyond cross-sectional scope. C is wrong because meta-analysis combines completed studies. The scenario describes ongoing data collection inside one system. D is wrong because randomized controlled trials assign interventions to participants. The scenario observes ED volume without applying any intervention. Time series analysis is a method for studying how aggregated metrics change over time. Not individual people, but system-level measures tracked at regular intervals. Its core purposes are detecting trends, identifying seasonality, and forecasting future values. Analysts decompose a time series into 3 components: trend, the long-term direction of the data; seasonality, the recurring patterns within fixed cycles like weeks or years; and noise, the random variation left over. Separating these components is what makes forecasting possible. In practice, a health system might track ED visit volume every month for 5 years, 60 data points in chronological order. Decomposing that series reveals a winter peak, a summer trough, and a gradual upward trend, giving operations leaders a solid basis for staffing and capacity planning. The key exam trap is confusing time series analysis with longitudinal cohort studies. In a time series, the unit of analysis is the time point, and the data are aggregated metrics. In a cohort study, the unit is the individual person, and the focus is on clinical outcomes. Monthly ED visit counts is a time series. 5 years of follow-up for diabetic patients is a cohort. Signal words like monthly, quarterly, sequential observations, seasonality, and forecasting all point to time series analysis. When the unit of interest is the system rather than the person, time series is the right design. Question 24. A research team wants to synthesize evidence from 40 published trials on antihypertensive medication adherence to estimate a pooled effect size. Which research method fits? Your options are A. Cross-sectional study that captures a single moment. B. Case study that explores a single patient experience. C. Focus group that elicits perspectives from a small panel. D. Meta-analysis that combines results from multiple studies. Got a guess? Lock it in. The correct answer is D. Meta-analysis that combines results from multiple studies. D is correct because meta-analysis is a systematic method for combining results across multiple existing studies to estimate a single pooled effect size. With 40 trials already published, the team has the raw material a meta-analysis needs. Greater statistical power is the central benefit. A is wrong because a cross-sectional study would generate new data from one point in time, not synthesize existing studies. B is wrong because a case study explores a single patient or institution in depth and does not produce population-level estimates. C is wrong because a focus group gathers qualitative perspectives from a small panel of participants. It does not pool quantitative outcomes across trials. Meta-analysis is a quantitative method that combines results from multiple studies into a single pooled estimate. It sits at the top of most evidence hierarchies because it draws statistical power from many studies at once, overcoming the limits of any single trial. Each included study contributes an effect size, a relative risk, odds ratio, or mean difference. Studies are weighted by the inverse of their variance, so larger, more precise studies count more. The output is a single summary effect with a narrower confidence interval than any individual study could produce. Rigorous meta-analyses follow strict protocols. These include a pre-registered review question, a comprehensive literature search, and a structured quality assessment of every included study. These safeguards, formalized by the Cochrane collaboration in the 1990s, separate trustworthy syntheses from unreliable ones. The key exam trap is assuming every meta-analysis is correct. A meta-analysis of biased studies produces a precisely biased estimate. Publication bias distorts results when significant findings are overrepresented. Tools like funnel plots and sensitivity analyses help detect these problems, but only when carefully applied. Meta-analysis synthesizes existing evidence. That is its defining feature. A narrative review describes the literature without statistical pooling. A primary study generates fresh data. On exam stems, the signal is plural, completed studies being combined into a pooled estimate. That description points exclusively to meta-analysis. Question 25. A pharmaceutical company evaluates a new asthma inhaler by randomly assigning participants to receive either the new device or a placebo. Outcomes are monitored over 12 weeks. Which study design is this? Your options are A. Randomized control trial with random assignment and an intervention. B. Cross-sectional study with 1 point of measurement. C. Time series analysis of sequential observations. D. Case study of a single patient's experience. Which one is it? Pause the video if you need more time. The correct answer is A. Randomized control trial with random assignment and an intervention. A is correct because a randomized controlled trial assigns participants to either the experimental intervention or a control through random allocation, then compares outcomes between groups. The new inhaler against a placebo with random assignment is the canonical RCT design. Randomization is the feature that minimizes selection bias. B is wrong because a cross-sectional study lacks both intervention assignment and follow-up over time. The trial has both. C is wrong because time series analysis tracks one metric repeatedly across intervals on the same unit. The trial compares two groups, not one ongoing measurement. D is wrong because a case study focuses on one patient or institution. The trial enrolls many participants in two arms. The randomized control trial is medicine's gold standard for establishing that an intervention actually causes an effect, not just correlates with one. 3 features define the design: random assignment of participants to groups, a control condition for comparison, and blinding of participants, providers, and analysts to reduce bias. Together, these features let researchers isolate the effects of the intervention. After random assignment, both groups are followed under identical protocols, same measurements, same intervals. At the end, outcomes are compared. Randomization ensures that any difference between groups reflects the intervention, not pre-existing differences at baseline. A randomized design does not guarantee unbiased results. Loss to follow-up, protocol violations, and unblinded outcome assessment can all compromise a trial. And remember, not every clinical trial is randomized. Non-randomized and observational designs carry higher confounding risk. When an exam stem describes participants assigned to groups by chance and followed under a protocol that is an RCT, randomization is what purchases causal inference. No other study design can match it for establishing efficacy. Question 20. A small clinic stores patient appointments in a single sheet with one row per patient and columns for date, time, and provider. There are no linked tables and no foreign keys. Which database type is this? Your options are A. Relational database with linked tables. B. Multidimensional database for ad hoc reporting. C. Flat file database with a single table structure. D. Data warehouse for cross-organization sharing. Take a second. Which answer would you pick? The correct answer is C. Flat file database with a single table structure. C is correct because a flat file database stores all information in one table with no relationships to other tables, much like a spreadsheet. The clinic's single sheet of appointments fits the definition perfectly. Flat files are simple, easy to read, and best for small, isolated datasets. A is wrong because a relational database connects multiple tables through key fields. Only one table exists in the scenario, ruling out a relational structure. B is wrong because a multi-dimensional database supports rapid analysis across multiple dimensions, typically for reporting cubes. A single appointment sheet does not provide that structure. D is wrong because a data warehouse stores enormous volumes of data for advanced analytics and cross-organization sharing. A small clinic with one sheet is far below that scale. A flat file database stores all data in a single table with no links to other tables. Think of it as the simplest possible database structure. One sheet, one list, no relationships. In a flat file, every appointment gets its own row. So if a patient has 3 visits, their name appears 3 times. A relational database instead links a single patient record to multiple visit records through a shared key, eliminating that repetition. Flat files earn their place because of simplicity. They are easy to inspect, backup, and transfer between systems. The cost is a lack of indexing, query power, and referential integrity. And updates are painful because every duplicate row must be changed individually. On exam day, watch for these signal words: single table, no relationships, spreadsheet style, and no foreign keys. If a stem describes one tabular structure with no internal linking, it is pointing at a flat file database. Remember, a multi-tab workbook with linked formulas is closer to a relational structure, not a flat file. Question 27. A regional hospital uses a database in which patient data, lab results, providers, and visits all live in separate tables linked by patient and visit identifiers. Which database type is this? Your options are A. Flat file database with one table. B. Relational database with linked tables connected by key fields. C. Object-oriented database for multimedia content. D. Data warehouse for historical analytics. Before I reveal it, which one do you think is right? The correct answer is B. Relational database with linked tables connected by key fields. B is correct because a relational database organizes data into multiple tables linked through shared key fields, like patient and visit identifiers. The hospital's designed with patients, labs, providers, and visits in separate but joined tables matches the relational model exactly. It is the most common database structure in modern healthcare information systems. A is wrong because a flat file holds one table with no relationships. The hospital has many tables linked together, which exceeds the flat file design. C is wrong because an object-oriented database is built around storing complex objects, often including multimedia like images, audio, and video. The hospital scenario describes structured tabular data only. D is wrong because a data warehouse aggregates data from many transactional sources for analytics. The scenario describes operational tables, not an analytics aggregate. The relational model is the backbone of operational data storage in healthcare IT. It organizes information into multiple linked tables, each representing a single type of entity connected through shared key fields. Every table has a primary key that uniquely identifies each row. A foreign key in a related table points back to that primary key. So patient details are stored exactly once and referenced from every visit record that belongs to that patient. Flat files repeat patient information on every visit row, creating redundancy and update headaches. The relational model stores each fact in exactly one place, so a single update to the patient record is instantly reflected everywhere it is referenced. The classic exam trap is confusing relational databases with multidimensional or data warehouse designs. Relational systems handle daily transactional operations with frequent updates, while multidimensional structures are optimized for infrequent, large-scale analytical queries. The workload type is the key discriminator. When a question stem describes multiple tables joined by identifiers, foreign keys, or structured query language, that is a signal for relational design, the operational workhorse of healthcare IT. Question 28. A health system analyst wants a database that can quickly produce ad hoc reports slicing patient outcomes by service line, payer, and time period at the same time. Which database type best fits? Your options are A. Flat file database limited to a single table. B. Object-oriented database for multimedia. C. Transactional database for real-time operations. D. Multi-dimensional database optimized for rapid multi-axis analysis. What's your answer? Commit to one before I continue. The correct answer is D. Multi-dimensional database optimized for rapid multi-axis analysis. D is correct because a multi-dimensional database is structured around analytical cubes, allowing rapid slicing and dicing of data across many dimensions such as service line, payer, and time. The need for fast ad hoc reports across multiple axes is the defining use case. Performance for analytics is the main advantage. A is wrong because a flat file is a single table with no inherent multi-axis indexing. Performance and flexibility would suffer at the scale described. B is wrong because an object-oriented database specializes in storing complex objects like images or video, not analytical slicing of tabular outcomes. C is wrong because a transactional database focuses on accurate, real-time recording of operational events and rollback safety. Ad hoc analytics is not the strength of that design. Multi-dimensional databases are purpose-built for fast analytical queries across many dimensions at once. Unlike relational databases that assemble data through joins at query time, multi-dimensional databases pre-compute the answers before anyone asks. The core structure is called a cube. Each axis of the cube represents a dimension, such as service line, time period, or payer, and each cell holds a value that has already been calculated and indexed. The mechanism is precomputation. When data lands in the cube, the system calculates totals, subtotals, and averages across every combination of dimensions, so results are already waiting when the analyst asks. The key contrast is with relational databases. Relational tables are normalized for write efficiency and integrity. Multi-dimensional cubes are denormalized for read efficiency and analytics. The same query that takes minutes on a relational source returns in seconds from a cube. On exam day, signal words like ad hoc reporting, slicing and dicing, OLAP cubes, and fast analytical queries all point to multi-dimensional design, when speed of analytical retrieval across multiple dimensions is the requirement. The multi-dimensional database is the answer. Question 29. A national consortium pools cancer treatment data from 60 hospitals into a single storage system for long-term research and benchmarking. Which database type fits the scale and purpose? Your options are A. Data warehouse capable of large-scale storage and cross-organization analytics. B. Flat file database stored as one master spreadsheet. C. Transactional database focused on real-time order entry. D. Disease registry limited to a single condition. Pick one. Trust your gut. Here's your chance to test yourself. The correct answer is A. Data warehouse capable of large-scale storage and cross-organization analytics. A is correct because a data warehouse is built to hold massive volumes of integrated data from many sources, with support for advanced analytics and cross-organization sharing. Pooling data from 60 hospitals for long-term benchmarking is exactly the workload data warehouses are designed for. Storage capacity and analytic flexibility are central. B is wrong because a flat file in spreadsheet format cannot handle the volume or relational complexity of 60 hospitals worth of cancer data. C is wrong because transactional databases are optimized for fast, single record operations such as order entry. Analytics across millions of pooled records is the opposite workload. D is wrong because a disease registry tracks one condition systematically and can be useful for surveillance, but the broader, federated, multi-organization analytic use case fits a warehouse better. A data warehouse is a large-scale repository that stores integrated historical data from many source systems for analytics and decision support. It forms the backbone of enterprise business intelligence across healthcare, finance, and other major industries. Operational databases are optimized for small, fast transactions. Analytical workloads require large reads and aggregate queries, the opposite pattern. Mixing both on one system degrades performance for each, which is exactly why the data warehouse was created as a separate layer. The extract, transform, load process, ETL, moves data from source systems into a staging area for cleansing and standardization. Transformed data lands in a star schema with fact tables surrounded by dimension tables. Reports and dashboards then query the warehouse directly, leaving operational systems free for their primary work. On exam day, watch for these signal terms: historical analytics, large-scale storage, cross-organization data, consolidated sources, enterprise reporting, and data mining. Any stem describing a central repository pulling from many sources for analysis is pointing at the data warehouse. The warehouse is the foundation of the analytical stack. Operational systems feed it, analytical tools query it, and cubes accelerate specific reporting on top of it. It stores history, it does not run transactions. Question 30. A clinical informatics director must choose a system for storing radiology images, dictated reports, and embedded audio annotations alongside structured patient identifiers. Which database type best supports this mixed content? Your options are A. Flat file database with simple text columns. B. Relational database alone without multimedia support. C. Object-oriented database designed to store rich multimedia objects. D. Time series database optimized for sequential numeric measurements. Which would you go with? Lock it in before the reveal. The correct answer is C. Object-oriented database designed to store rich multimedia objects. C is correct because an object-oriented database stores complex objects including audio, video, and image data alongside structured fields, radiology images, dictated audio, and patient metadata together require a structure that handles mixed content as cohesive objects. Electronic health records often rely on this design where multimedia is central. A is wrong because a flat file with simple text columns cannot natively store images or audio in a queryable form. Multimedia would need to live elsewhere. B is wrong because a pure relational design is excellent for structured data, but typically requires bolt-on storage solutions for multimedia. The object-oriented model is purpose-built for it. D is wrong because a time series database is tuned for sequential numeric values, such as monitoring readings, not for image and audio storage. Object-oriented databases are built to store complex objects that combine structured fields, multimedia, and text as a single coherent unit. This is fundamentally different from how relational databases work, and understanding that difference is the key insight. Each object in the database keeps its attributes, methods, and relationships intact. The database natively supports inheritance and polymorphism, the same concepts used in object-oriented programming languages. Consider a radiology study object containing patient identifiers, image data, a dictated report, and audio annotations all linked as one entity. Retrieving it returns the whole object at once, with no need to join across multiple relational tables. The cleanest contrast is this. Relational databases store flat tabular rows and handle multimedia owner as unstructured binaries, blobs in columns, requiring joins to reassemble related data. Object-oriented databases store the full structure natively, eliminating that impedance mismatch. When an exam stem describes rich multimedia content, images, audio, video, stored alongside structured data as part of a clinical record that is pointing at an object-oriented database. The design judgment is simple. If the data is fundamentally object-like rather than tabular, the object-oriented model fits. Question 31. A state cancer program collects detailed information on every newly diagnosed malignancy in the state for surveillance and reporting purposes. Which type of database structure best describes this? Your options are a flat file database with one master sheet, B. Transactional database with rollback features, C. Data warehouse aggregating financial data, D. Disease registry that tracks cases of one specific condition. Don't overthink it. Which one feels right? The correct answer is D. Disease registry that tracks cases of one specific condition. D is correct because a disease registry collects standardized data on every case of a specific condition within a defined population, supporting surveillance, public health reporting, and research. A cancer registry is a long-standing example. The case-specific design is what separates registries from broader databases. A is wrong because a flat file is a generic structure with limited functionality and is not the purpose-built tool for surveillance of a condition. B is wrong because transactional databases focus on real-time operations such as order entry, not population-level disease tracking. C is wrong because data warehouses aggregate diverse data for analytics, often including financial information, but they are not specific to a single condition the way a registry is. A disease registry is a specialized database that systematically captures every case of a defined condition within a defined population. Understanding what makes registries unique helps distinguish them from other data systems you'll encounter on the exam. Registries serve four main purposes: public health surveillance, clinical research, quality improvement, and policy planning. Familiar examples include cancer registries, trauma registries, organ transplant registries, and rare disease registries, each built around one specific condition. Hospitals, clinics, and laboratories submit standardized records on every qualifying case. Registry staff verify records, remove duplicates, and link with vital statistics, creating a population-level data set that tracks patients from diagnosis all the way to death. The critical exam distinction is that a registry is condition-specific and population-based. It stores elements relevant to one condition for every case. A data warehouse aggregates many kinds of data across many conditions. If the database is built around one condition, it's a registry. When an exam stem describes a database focused on a single disease, capturing every case in a defined population, that's a registry. The condition-specific, population-based focus is the defining feature that separates registries from warehouses and electronic health records. Question 32. A hospital pharmacy needs a database that records every medication dispensed in real time, supports rollback if a transaction fails, and enforces strict consistency across linked tables. Which database type best fits? Your options are a multidimensional database designed for ad hoc reporting, B. Transactional database designed for real-time operational consistency, C. Disease registry tracking medication-related conditions, D. Data warehouse storing decade-long pharmacy archives. Got a guess? Lock it in. The correct answer is B. Transactional database designed for real-time operational consistency. B is correct because a transactional database is optimized for real-time operations with strict consistency and rollback safety, so that no half-completed transaction corrupts the data. A pharmacy needs every dispense to be recorded atomically, with the ability to undo a failed entry. That operational profile is the heart of transactional design. A is wrong because a multidimensional database is built for analytical slicing across reporting cubes, not for atomic real-time transactions. C is wrong because a disease registry tracks cases of a specific condition for surveillance. It is not engineered for moment-to-moment pharmacy operations. D is wrong because a data warehouse holds large analytical archives but is generally not the system handling live transactions. Transactional databases are built for real-time, mission-critical operations where every write must be accurate and complete. The foundation of this reliability is a set of 4 guarantees known as ACID properties. Atomicity ensures no partial updates ever persist. Consistency means the database is always valid before and after a transaction. Isolation keeps simultaneous transactions from corrupting each other. And durability guarantees committed data is never lost, even if the system crashes. In practice, a single pharmacy dispense touches multiple tables at once: inventory, billing, the dispense log, and the medication administration record. If any step fails, the entire transaction rolls back, preventing partial updates that could have real clinical consequences. The key exam distinction is purpose. Transactional databases prioritize write speed and consistency to run live operations. Analytical databases prioritize read speed and aggregation to study historical data. Mixing the two workloads degrades performance and risks inconsistency. When an exam stem describes real-time operations, rollback, or strict consistency, the answer points to a transactional database. When it describes reporting, trends, or aggregation, think analytical structures like data warehouses. Question 33. A medical staff office is credentialing a new physician and needs to check whether the candidate has any history of malpractice payments or adverse licensure actions. Which national data source is the appropriate place to look? Your options are A. HCA-HPS, which collects patient experience information, B. CDC, which publishes morbidity and mortality statistics, C. NPDB, which maintains records of malpractice and licensure actions, D. CMS, which manages Medicare and Medicaid reimbursement data. Which one is it? Pause the video if you need more time. The correct answer is C. NPDB, which maintains records of malpractice and licensure actions. C is correct because the National Practitioner Data Bank, known as NPDB, collects malpractice payments, adverse licensure actions, and other disciplinary information on physicians and other providers. It exists specifically to support credentialing decisions like this one. Health systems query it as a standard part of provider onboarding. A is wrong because HCAHPS focuses on patient satisfaction with hospital stays, not on practitioner discipline histories. B is wrong because the CDC publishes population-level disease surveillance and vital statistics, but does not maintain practitioner credentialing records. D is wrong because CMS data covers reimbursement, hospital quality scores, and Medicare and Medicaid claims, but the malpractice and licensure focus lives in NPDB. The National Practitioner Data Bank is a federal repository created in 1986 by the Healthcare Quality Improvement Act. Its core purpose is to prevent practitioners with disciplinary histories from moving across state lines without disclosure. Reporting is mandatory for 4 main categories: medical malpractice payments, adverse licensure actions, adverse clinical privileges actions, and professional society membership actions. Malpractice payers must report within 30 days of settlement, and hospitals must report privileges, actions lasting longer than 30 days. Credentialing organizations must query the data bank at initial credentialing and every 2 years thereafter for hospital-affiliated clinicians. Critically, failure to query carries a legal presumption that the organization already knew of any reported events. In practice, a credentialing office submits a query for a specific practitioner and receives a report of all matching records across that practitioner's entire career. The committee reviews this report alongside training records and references before granting privileges. The exam day discriminator is matching the right repository to the right need. The CDC handles population health, CMS handles program administration, and HCAHPS captures patient satisfaction. The data bank is the only source for practitioner level discipline and malpractice information. Question 34. A public health researcher wants the most authoritative national source for US data on births, deaths, marriages, and disease surveillance. Which agency is the appropriate place to look? Your options are A. CDC, which maintains national vital statistics and disease surveillance. B. NPDB, which tracks malpractice payments and licensure actions. C. HCAHPS, which surveys patient experience in hospitals. D. AHRQ, which publishes research on clinical quality and safety. Take a second. Which answer would you pick? The correct answer is A. CDC, which maintains national vital statistics and disease surveillance. A is correct because the Centers for Disease Control and Prevention is the federal agency responsible for collecting and publishing vital statistics such as births and deaths, along with morbidity and mortality data and disease surveillance reports. National vital records flow through the CDC pipeline. Researchers needing the most authoritative national source go there first. B is wrong because NPDB is limited to practitioner disciplinary history and does not collect vital statistics. C is wrong because HCAHPS focuses on hospital consumer assessment surveys, not on births or deaths. D is wrong because AHRQ produces health services, research and quality indicators but does not serve as the national vital statistics repository. The Centers for Disease Control and Prevention is the United States federal agency dedicated to population health surveillance and prevention. Understanding exactly what the CDC owns and what it does not is essential for answering data source questions correctly. The CDC is the authoritative national source for vital statistics and disease data. It collects births, deaths, marriages, and divorces through the National Vital Statistics System and monitors morbidity and mortality across infectious and chronic conditions. Data flows into the CDC from state and local health departments, hospitals, laboratories, and vital records offices. The agency aggregates, analyzes, and publishes findings, including the widely read Morbidity and Mortality Weekly Report, with privacy protections in place. The exam trap is assuming the CDC handles all federal health data. It does not. The Centers for Medicare and Medicaid Services owns reimbursement data. The National Practitioner Data Bank owns practitioner discipline, and the National Institutes of Health funds research. Each agency owns its niche. When a question stem mentions national vital statistics, births and deaths, morbidity and mortality, or outbreak investigation, it is pointing at the CDC. Recognizing those signal words and matching them to the right agency is the key skill here. Question 35. A health system finance leader wants to compare Medicare reimbursement rates and quality scores across competing hospitals in the region. Which national source publishes this data? Your options are A. NPDB, which manages malpractice records, B. CMS, which maintains Medicare and Medicaid reimbursement and quality data, C. CDC, which publishes disease surveillance, D. HCA-HPS, which contains only patient experience surveys. Before I reveal it, which one do you think is right? The correct answer is B. CMS, which maintains Medicare and Medicaid reimbursement and quality data. B is correct because the Centers for Medicare and Medicaid Services administers Medicare and Medicaid and publishes reimbursement data along with hospital quality scores used for value-based purchasing. A finance leader benchmarking reimbursement and quality across hospitals will draw on CMS reports. The agency is the central source for both topics. A is wrong because NPDB focuses on practitioner discipline records, not financial reimbursement or hospital quality. C is wrong because the CDC publishes disease surveillance and vital statistics, but does not set or report Medicare reimbursement. D is wrong because HCA-HPS contains patient experience data, which is one component within CMS quality reporting, but reimbursement comparisons require the broader CMS dataset. The Centers for Medicare and Medicaid Services is far more than a billing office. It is the largest single payer in the U.S. healthcare system and a primary source of data for researchers, leaders, and policymakers. CMS directly administers Medicare, Medicaid, the Children's Health Insurance Program, and the federal exchanges created by the Affordable Care Act, because its coverage decisions and reimbursement rules shape provider behavior. Even providers who don't accept Medicare often follow its standards, ICT, because commercial payers mirror them. Every Medicare claim, every nursing home survey, and every hospital quality submission flows into CMS data systems. That data drives payment, fraud detection, value-based purchasing programs, and public reporting on platforms like Care Compare. The most common exam trap is mixing up CMS with other federal agencies. Disease surveillance belongs to the CDC. Practitioner discipline belongs to the National Practitioner Data Bank. Reimbursement rates and hospital quality scores belong to CMS. When an exam stem mentions Medicare reimbursement, hospital quality star ratings, or value-based purchasing, that is pointing directly at CMS, not the CDC, not the data bank, and not any other agency. Question 36. A hospital quality director wants to measure how patients perceive their hospital stays through a standardized national survey required by CMS. Which instrument should the director use? Your options are A. NPDB, which tracks practitioner discipline records, B. Cancer Registry, which collects oncology case details, C. Chi-square test, which evaluates categorical association. D. HCAHPS, which standardizes patient experience reporting nationwide. What's your answer? Commit to one before I continue. The correct answer is D. HCAHPS, which standardizes patient experience reporting nationwide. D is correct because the Hospital Consumer Assessment of Healthcare Providers and Systems is a standardized survey that asks discharged patients about their hospital stays, including communication, responsiveness, and cleanliness. CMS requires HCHPS reporting, and results feed into national rankings and value-based payment. It is the standard tool for the director's purpose. A is wrong because NPDB tracks provider disciplinary actions, not patient perceptions. B is wrong because a cancer registry collects clinical oncology data, not patient experience. C is wrong because Chi-square is a statistical test, not a data collection instrument. HCAHPS is the national standardized survey that measures how patients perceive their hospital experience. Understanding what it covers, how it works, and why it matters is essential for healthcare quality discussions. The survey's 29 items span 8 domains: nurse communication, doctor communication, staff responsiveness, hospital cleanliness, pain management, medicine communication, discharge information, and an overall hospital rating. Each month, participating hospitals randomly sample discharged patients and administer the survey through approved channels. Results are submitted to CMS, risk adjusted, and reported publicly as top box scores. The percentage of patients answering always or strongly agree, preventing grade inflation from simple averages. The key distinction is that HCAHPS captures patient perception of care, not clinical outcomes like infection rates or mortality. Both types feed into value-based purchasing, but HCAHPS is the only federally required, nationally comparable instrument for the patient experience dimension. When a question describes a national, standardized patient experience instrument tied to Medicare reporting, that's HCAHPS. It's the benchmark for perception, distinct from clinical outcome metrics, and the only survey required for federal reporting. Question 37. An infection prevention nurse is reviewing 2 metrics. The first counts central line infections in patients with intravenous lines, and the second counts urinary infections in patients with indwelling catheters. Which pair of acronyms identifies these 2 metrics? Your options are A. HCHPS and NPDB, used for patient experience and credentialing. B. CMS and CDC, used for reimbursement and surveillance. C. CLABSA and CAUTI, 2 clinical quality indicators tracked by CMS and the CDC. D. ANOVA and Chi-square, 2 statistical tests for categorical data. Pick one. Trust your gut. Here's your chance to test yourself. The correct answer is C. CLABSI and CAUTI, 2 clinical quality indicators tracked by CMS and the CDC. C is correct because CLABSI stands for Central Line Associated Bloodstream Infection and tracks infections among patients with intravenous central lines. CAUTI stands for Catheter Associated Urinary Tract Infection and tracks infections among patients with indwelling urinary catheters. Both are mandatory quality indicators in infection prevention programs. A is wrong because HCAHPS measures patient experience and NPDB tracks practitioner discipline. Neither is an infection metric. B is wrong because CMS and CDC are federal agencies, not specific infection metrics. D is wrong because ANOVA and Chi-square are statistical tests, not infection rate metrics. 2 of the most important clinical quality indicators in hospital care are CLABSI and CAUTI, both device-associated infections that are largely preventable and closely tracked by federal agencies. CLABSI stands for Central Line Associated Bloodstream Infection, tracking infections in patients with central venous catheters. CAR-T stands for Catheter Associated Urinary Tract Infection, tracking infections in patients with indwelling urinary catheters. The device type determines which metric applies. Each infection is tied directly to a specific device. The central line provides a pathway for pathogens into the bloodstream, while the indwelling urinary catheter introduces risk of bacterial colonization in the urinary tract. Both infections are measured using standardized NHSN definitions, which allow fair comparison across hospitals and over time. Rates are expressed per 1,000 device days to control for differences in how often devices are used, and they are reported publicly through Hospital Compare. It is important to recognize that CLABSI and CAR-T are outcome metrics. They count actual infections that occurred. Process metrics like hand hygiene, compliance measure behavior, and perception metrics like patient satisfaction surveys measure experience. Knowing this distinction is essential for mastering healthcare quality measurement. Question 38. A hospital finance team wants a single statistic that summarizes the typical billed charge across 100,000 encounters. The team also wants to capture the influence of unusually high charges. Which measure of central tendency fits? Your options are A. The arithmetic mean, which is influenced by extreme values. B. The mode, which captures only the most frequent value. C. The median, which is resistant to outliers and ignores their magnitude. D. The range, which is a measure of spread rather than tendency. Which would you go with? Lock it in before the reveal. The correct answer is A. The arithmetic mean, which is influenced by extreme values. A is correct because the arithmetic mean is calculated by summing all values and dividing by the count. So every observation contributes proportionally. When the analyst wants outliers to influence the summary statistic, the mean is the appropriate measure. High charges pull the mean upward in a way the team can detect. B is wrong because the mode reports only the most common value and provides no information on extreme charges. C is wrong because the median is the middle value and ignores the magnitude of outliers entirely. The team wants those high charges reflected, not suppressed. D is wrong because the range describes spread between minimum and maximum and does not summarize the central tendency of the distribution. The arithmetic mean is the most fundamental measure of central tendency in statistics. Understanding when to use it, and when not to, is one of the most tested concepts on quantitative exams. The mean is computed by summing all observations and dividing by the count. It works best with interval and ratio data where arithmetic operations are meaningful. Its key property and its key weakness is that every value influences it equally, including extreme outliers. In a right-skewed distribution, like hospital charges or income, a long tail of high values pulls the mean upward. The median, by contrast, marks the middle rank and is unaffected by how extreme those outliers actually are. The mean, median, and mode each capture a different sense of typical. The mean is sensitive to every value. The median is sensitive only to rank. The mode is sensitive only to frequency. Choosing among them depends on whether outlier influence is useful or misleading for your specific question. On exam day, watch for stems describing summed and divided summaries, or phrases about extreme values pulling the result. When outlier influence is exactly what the analysis wants to capture, the mean is the correct choice. Question 39. A pediatric clinic measures the spread of patient ages around the mean by computing the typical distance of any single observation from the average. Which statistic does this describe? Your options are A. The median, which marks the middle of the distribution. B, the mode, which marks the most frequent value. C, the range, which marks the difference between extremes. D, the standard deviation, which marks the typical distance from the mean. Don't overthink it. Which one feels right? The correct answer is D. The standard deviation, which marks the typical distance from the mean. D is correct because standard deviation quantifies how far observations typically fall from the mean of a data set. A small standard deviation indicates values cluster close to the average, while a large standard deviation signals widespread. The clinic's interest in typical distance from the average is exactly what standard deviation reports. A is wrong because the median marks the central value but says nothing about spread or distance from the mean. B is wrong because the mode reports the most frequent value and offers no measure of variability. C is wrong because the range is the simplest spread measure but reflects only the extremes, not the typical deviation from the average. The standard deviation measures how far observations typically fall from the mean. It's the most important measure of spread in statistics. Understanding how it's built helps you use it correctly and avoid common exam traps. For each observation, you subtract the mean to get a deviation, then square it so values stay positive and larger gaps are emphasized more. Average those squared deviations to get the variance. Then take the square root to bring the result back into the original units. That final number is the standard deviation. In a normally distributed dataset, about 68% of observations fall within one standard deviation of the mean, about 95% within 2, and about 99.7% within 3. This predictable pattern is why the standard deviation underlies most parametric statistical tests. The range is simply maximum minus minimum and is highly sensitive to outliers. The interquartile range covers the middle 50% and resists outliers. The variance is the standard deviation squared, leaving it in squared units that are hard to interpret. The standard deviation strikes the best balance between interpretability and sensitivity to spread. Whenever an exam stem asks how tightly values cluster around the average, or how widely they spread, it is pointing at standard deviation. Together with the mean, it gives you the two most essential descriptive statistics for any interval or ratio dataset. Question 40. A managed care plan reports that the most common diagnosis code among 1 year of claims is a routine annual physical visit. Which measure of central tendency does this finding describe? Your options are A, the mean, which averages numeric values. B, the mode, which reports the most frequent value. C, the median, which reports the middle value. D, the standard deviation, which reports the spread. Got a guess? Lock it in. The correct answer is B, the mode, which reports the most frequent value. B is correct because the mode is the value that occurs most often in a data set. When a managed care plan identifies the most common diagnosis code, it is reporting the mode of the diagnostic category column. Mode is the only central tendency that works on nominal data like diagnosis codes. A is wrong because the mean requires numeric data and cannot be calculated on categorical diagnosis codes. C is wrong because the median requires data that can be ranked, but diagnosis codes are nominal categories without inherent order. D is wrong because standard deviation is a measure of spread, not central tendency, and also requires numeric data. The mode is the most frequently occurring value in a data set. Unlike the mean or median, it requires no arithmetic, just counting. That simple property makes it uniquely powerful for certain types of data. Nominal data uses labels without numeric meaning. Think diagnosis codes or carrier names. You can't average a label or find its middle value, so the mean and median simply don't apply. The mode survives that restriction because it only needs to count occurrences. The frequency count mechanism is straightforward. Tally each unique value and find the highest count. A dataset can be unimodal with one peak, bimodal with two equally frequent values, or multimodal with three or more. In some datasets, every value appears once and no mode exists. Visually, the mode is simply the tallest bar in a frequency chart. For a column of insurance carrier names, whichever carrier name appears most often is the mode. Waxet guida, no math beyond counting required. When choosing among the three measures, match the statistic to the data type. The mean needs numeric data and is sensitive to every value. The median needs ordered data. The mode needs only countable categories. For nominal data, the mode is the only sensible choice, and it often delivers the most actionable insight about utilization patterns or common categories. Question 41. A national hospital ranking system compares mortality rates across facilities. A teaching hospital with the sickest patients argues the raw rates are misleading and asks for a fairer comparison. Which analytical technique addresses this concern? Your options are A. Time series analysis to detect mortality trends. B. Pearson correlation to measure relationship strength. C. Risk adjustment to control for patient complexity. D. Cross-sectional sampling to estimate prevalence. Which one is it? Pause the video if you need more time. The correct answer is C. Risk adjustment to control for patient complexity. C is correct because risk adjustment uses statistical methods, often multivariate regression, to account for differences in patient complexity, severity, and case mix before comparing outcomes across systems. Without it, hospitals serving sicker populations look worse simply because their patients carry more risk. Risk adjustment is essential for fair benchmarking. A is wrong because time series analysis identifies changes in one metric across intervals but does not control for patient mix differences between hospitals. B is wrong because Pearson correlation measures the strength of association between two variables and does not adjust outcomes for complexity. D is wrong because cross-sectional sampling captures prevalence at one moment but does not remove the influence of patient acuity from outcome comparisons. Risk adjustment is the technique that levels the playing field when comparing hospitals or providers. Without it, a hospital serving sicker patients looks worse on paper, even if it delivers excellent care. The goal is to make comparisons fair by accounting for patient mix before publishing results. Raw outcome rates are misleading because patient populations differ in age, comorbidities, severity, and social risk. A hospital treating the highest risk patients will naturally show higher mortality. That difference reflects case mix, not care quality. The mechanism is multivariate regression. A statistical model uses patient characteristics to produce an expected outcome rate. Dividing the observed rate by the expected rate yields the risk-adjusted ratio. Above 1 means worse than expected for that patient mix. Below 1 means better. Risk adjustment does not solve every problem. It can only control for factors actually measured in the model. Unmeasured frailty and incomplete claims data still distort results. Hospitals may also game the system through upcoding, coding more diagnoses to inflate complexity scores and lower their expected rates. The core insight is simple. Compare like to like. Risk adjustment is preferred when many factors must be controlled simultaneously and a single summary number per hospital is needed. Recognizing both its value and its limits is essential for any quality measurement context. Question 42. A regional health system wants to forecast which of its discharged patients are most likely to return within 30 days, so it can target outreach. Which analytical technique fits this need? Your options are A. Predictive modeling that uses algorithms to estimate probability of future outcomes. B. Meta-analysis that pulls prior published findings. C. Cross-sectional study that samples patients at one moment. D. Range calculation that summarizes minimum and maximum stay length. Take a second. Which answer would you pick? The correct answer is A. Predictive modeling that uses algorithms to estimate probability of future outcomes. A is correct because predictive modeling uses mathematical algorithm applied to historical data to estimate the probability of a future event, such as a 30-day readmission. The output is a risk score that targets outreach to patients most likely to need it. This is the standard analytical approach for proactive case management. B is wrong because meta-analysis combines existing studies for a pooled effects size, but does not generate individualized predictions for current patients. C is wrong because a cross-sectional study captures a snapshot of a population and is not designed to forecast individual outcomes. D is wrong because range describes the spread between minimum and maximum and offers no predictive information about individual patients. Predictive modeling uses mathematical algorithms applied to historical data to estimate the probability that a future event will occur. It sits at the heart of population health management, case management, and operational planning, helping organizations act proactively rather than reactively. It helps to place predictive modeling among its neighbors. Descriptive analytics summarizes the past. Predictive modeling forecasts the future. Prescriptive analytics recommends actions. Predictive modeling sits between the two. It looks at history to forecast outcomes but does not, by itself, tell you what intervention to apply. The mechanism follows a consistent pattern. Historical data is split into training and testing sets. The model learns a function on the training set, is validated on the testing set, and is then deployed to score new cases as they arrive, with high-risk scores triggering targeted interventions. A critical exam distinction: predictive modeling is not causal inference. Knowing that a patient carries a high readmission risk score does not reveal which intervention will reduce that risk. Causality requires different methods entirely, though the model simply ranks likelihood, not mechanism. When an exam stem describes a team wanting to anticipate which individuals are at high risk for a future outcome, that is predictive modeling. Signal words include risk score, probability, algorithm, machine learning, early identification, and forecasting. Question 43. A researcher is finalizing a study protocol and wants to confirm that participants understand the study and can choose freely whether to enroll. Which ethical principle most directly governs this concern? Your options are: A. Beneficence, which focuses on promoting welfare of participants. B. Autonomy, which protects the right of each participant to choose freely. C. Non-maleficence, which obliges researchers to avoid harm. D. Justice, which addresses fair selection across populations. Before I reveal it, which one do you think is right? The correct answer is B. Autonomy, which protects the right of each participant to choose freely. B is correct because autonomy is the ethical principle protecting each person's right to make informed decisions about participation in research. Informed consent is the procedural expression of autonomy. Ensuring participants understand the study and choose freely is the working definition of respecting autonomy. A is wrong because beneficence focuses on actively promoting participant welfare, which is related but broader. The question is specifically about voluntary informed choice. C is wrong because non-maleficence is the duty to avoid causing harm. The concern in the scenario is about voluntary participation, not about preventing harm. D is wrong because justice concerns the fair distribution of risks and benefits across populations, not the individual decision to enroll. Autonomy is the foundational ethical principle protecting an individual's right to make informed decisions about their own care and research participation. Understanding it means understanding how modern research ethics was built and why it matters. The modern autonomy principle traces directly to the Belmont Report of 1979, which was itself a direct response to the Tuskegee syphilis study, where men were observed for 40 years without consent or treatment. The Belmont Report formalized respect for persons, beneficence, and justice as the pillars of research ethics. Autonomy is operationalized through informed consent. The consent document must disclose all material information, be written accessibly, and affirm the participant's unconditional right to withdraw. Populations with limited consent capacity, including children, prisoners, and those with cognitive impairment, receive additional protections. Autonomy sits alongside three other principles: beneficence, non-maleficence, and justice. The critical exam distinction is this: autonomy is about the participant's agency and choice, while beneficence and non-maleficence focus on what the researcher does to or for the participant. A beneficial intervention performed without consent violates autonomy even if it satisfies beneficence. When a STEM describes ensuring participants understand a study and can freely agree or decline, that is autonomy. Signal phrases include informed consent, voluntary participation, self-determination, and right to withdraw. Autonomy generally takes precedence when it conflicts with paternalistic instincts. Question 44. A clinical research team is debating two ethical principles. One demands the active promotion of participant welfare, while the other demands the active avoidance of harm. Which option correctly labels the principle of avoiding harm? Your options are: A. Autonomy refers to the right of self-determination. B. Justice refers to equitable distribution of benefits. C. Beneficence refers to promoting participant welfare. D. Non-maleficence refers to the obligation to do no harm. What's your answer? Commit to one before I continue. The correct answer is D. Non-maleficence refers to the obligation to do no harm. D is correct because non-maleficence is the ethical obligation to avoid causing harm, often summarized as do no harm. It is paired with but distinct from beneficence, which is the duty to actively promote welfare. Together they form the two-sided obligation of researchers and clinicians. A is wrong because autonomy concerns the participant's right to make informed decisions, not the researcher's obligation to avoid harm. B is wrong because justice deals with the fair selection of participants and equitable distribution of benefits and risk across populations. C is wrong because beneficence is the active promotion of welfare, which is the partner concept, not the principle that targets avoidance of harm. Non-maleficence is the ethical obligation to avoid causing harm. It goes beyond the simple phrase, do no harm. It requires systematically weighing potential harms against potential benefits before acting. Non-maleficence is one of four pillars of biomedical ethics alongside autonomy, beneficence, and justice. It sits in productive tension with beneficence. Beneficence obligates you to do good, while non-maleficence obligates you to refrain from causing harm. They are related but not identical. The key exam trap is treating these two as identical. Non-maleficence means not causing harm. Sometimes the ethically correct choice is doing nothing. Beneficence means actively producing good. A clinician who avoids a high-risk intervention for a frail patient is honoring non-maleficence, even if a beneficence lens might favor more aggressive treatment. In practice, non-maleficence is operationalized through structured weighing, not absolute prohibition. In research, the IRB evaluates protocols to ensure benefits justify risks. In clinical care, informed consent gives patients the information to judge acceptable risk. A data safety monitoring board can stop a study early if harms exceed expected levels. When an exam STEM describes avoiding harm, minimizing risk, or protecting participants from injury. It is signaling non-maleficence, the negative obligation to refrain from harming, distinct from the positive obligation to help. Question 45. A study is recruiting participants exclusively from a single low-income community, despite the intervention being intended to benefit a broader population. Which ethical principle is this practice most likely violating? Your options are A. Autonomy, because participants must consent freely. B. Non-maleficence, because investigators must avoid harm. C. Justice, because benefits and risks must be distributed fairly. D. Fidelity, because researchers must keep their promises. Pick one. Trust your gut. Here's your chance to test yourself. The correct answer is C. Justice, because benefits and risks must be distributed fairly. C is correct because justice in research ethics requires fair selection of participants and equitable distribution of the burdens and benefits of research. Recruiting solely from a low-income community shifts the risk burden onto that population while spreading any benefit across a broader group. That uneven distribution is the core justice concern. A is wrong because autonomy addresses informed and voluntary consent, not population-level fairness of recruitment. B is wrong because non-maleficence focuses on avoiding harm to individual participants, not on how a population is sampled. D is wrong because fidelity concerns loyalty, truthfulness, and keeping promises to participants, which is distinct from the equity of selection. Justice in research ethics is about fairness at the population level, who bears the burdens of research and who receives its benefits. It operates on a different lens than the other ethical principles, looking at groups rather than individuals. Justice requires that no single community, especially a vulnerable one, shoulders the risks of research while a broader population enjoys the rewards. Institutional review boards operationalize this by scrutinizing who is recruited, how, and why. The justice principle emerged directly from historical abuses, the Tuskegee syphilis study, Nazi medical experiments on prisoners, and clinical trials in developing countries where participants would never access the resulting therapies. Each abuse drove the reforms we now take for granted. The classic exam trap is confusing justice with autonomy. Autonomy protects the individual's right to choose. Justice operates at the population level. A study can fully respect every participant's autonomy while still violating justice by systematically drawing from one vulnerable community. When a STEM describes concerns about which groups are enrolled or who benefits from results, that is a justice question. Look for signal phrases like fair selection, equitable distribution, and who bears the burdens. And remember, the unit of analysis is the group, not the person. Question 46. A nursing director wants to use data on patient falls, medication errors, and discharge timeliness to identify weak points in a unit and run small tests of change. Which application of analytics is this? Your options are A. Quality improvement, which uses data to drive process change. B. Predictive modeling, which forecasts future individual outcomes. C. Meta-analysis, which combines published trial results. D. Risk adjustment, which controls for patient complexity. Which would you go with? Lock it in before the reveal. The correct answer is A. Quality improvement, which uses data to drive process change. A is correct because quality improvement is the application of data and analytic techniques to identify performance gaps, design targeted interventions, and verify whether those interventions move outcomes. Reviewing falls, errors, and discharge timing to test small changes is a textbook quality improvement cycle. The discipline relies heavily on benchmarking and outcome evaluation. B is wrong because predictive modeling forecasts individual probabilities and does not necessarily drive process redesign. C is wrong because meta-analysis synthesizes existing trial evidence and is not a unit-level improvement activity. D is wrong because risk adjustment controls for patient complexity in comparisons, which supports quality improvement but is not the activity itself. Quality improvement is a disciplined, continuous cycle of using data to identify performance gaps, design targeted interventions, and verify whether those interventions actually move outcomes. Unlike a one-time project, it never stops. Each cycle feeds the next. The discipline draws on 3 industrial process improvement methods adapted for healthcare: Plan, Do, Study, Act, Lean methodology, and Six Sigma. Modern programs blend these with clinical expertise and patient experience data. The mechanism is iterative. A team plans a change, tests it on a small scale, studies the measured results, and then acts, scaling what works, refining what partially works, or abandoning what doesn't. Multiple cycles often run in parallel, each targeting a specific aspect of the problem. The classic exam trap is confusing quality improvement with research. Both use data and structured methods, but QI generates local knowledge to improve one organization's processes under internal governance, while research generates generalizable knowledge for a wider audience under IRB oversight. What truly defines quality improvement is its closed loop, measurement, deliberate action, and follow-up measurement. Whenever an exam stem describes data-driven cycles of change, think PDSA, performance gaps, small tests of change. That signal points to quality improvement. Question 47. A health system administrator compares its readmission rate against the average rate of similar academic medical centers and a top dental peer cohort. Which analytical activity is this? Your options are: A. Risk adjustment that controls for patient complexity. B. Benchmarking that uses comparison points to evaluate performance. C. Stratification analysis that divides the population into subgroups. D. Confounding analysis that removes external variables. Don't overthink it. Which one feels right? The correct answer is B. Benchmarking that uses comparison points to evaluate performance. B is correct because benchmarking is the comparison of organizational performance against external reference points, such as peer averages and top performers, to identify gaps and improvement opportunities. Comparing readmission rates to similar academic centers and a top decile peer cohort is benchmarking by definition. It is a foundation of quality improvement. A is wrong because risk adjustment is the methodological step that makes benchmarking fair across hospitals of different complexity, but the activity described is the comparison itself. C is wrong because stratification divides one population into subgroups before sampling or analysis. It is a technique within studies, not external comparison. D is wrong because confounding analysis removes the influence of external variables that distort relationships. It is a different concept from external performance comparison. Benchmarking is the practice of comparing your organization's performance against external reference points, not just tracking your own progress over time, but understanding where you stand relative to peers, industry medians, and top performers. For any given metrics, analysts compare their organization's value against common distribution points, the median, the 75th or 90th percentile, and the top decile. A hospital that cut its infection rate from 5 to 3 per 1,000 catheter days has improved. But if the national median is 1 and the top decile is 0, the gap is still significant. Visually, benchmarking places your organization somewhere along a distribution. The goal of improvement initiatives is to move that position rightward, closing the gap toward the top decile over successive measurement periods. It helps to keep 3 concepts separate: Trend analysis is the internal view, how you changed over time. Benchmarking is the external comparison in where you stand relative to peers. Risk adjustment is the statistical technique that makes benchmarking fairer by controlling for differences in patient population and case mix. They work together but answer different questions. When an exam stem describes an organization evaluating performance against industry standards, peer groups, or percentile rankings, that is the signal for benchmarking. Use benchmarks as one input among many, not as the final word, because peer group selection and case mix differences always introduce some risk of unfair comparison. Question 48. A vice president of operations is reviewing two types of performance metrics. One predicts future performance through inputs like staff training hours and process compliance, while the other reflects outcomes that have already happened, like infection rates and mortality. Which option correctly labels the predictive metrics? Your options are A. Outcome indicators that measure final results. B. Confounders that distort statistical relationships. C. Statistical indicators that measure variance. D. Leading indicators that anticipate future performance. Got a guess? Lock it in. The correct answer is D. Leading indicators that anticipate future performance. D is correct because leading indicators are forward-looking metrics that predict future performance by measuring inputs and processes likely to drive outcomes. Staff training hours and compliance rates are leading because they precede the outcomes they influence. They are distinguished from lagging indicators, which describe results already achieved. A is wrong because outcome indicators measure final results and are lagging by nature, not predictive. B is wrong because confounders are statistical concepts about distorting variables, unrelated to predictive performance metrics. C is wrong because statistical indicators is not a standard category in the performance measurement vocabulary, and it does not capture the leading versus lagging distinction. Performance management relies on two complementary types of metrics. Understanding the difference between them is essential for making timely, effective decisions at every level of an organization. Leading indicators are forward-looking. They measure processes and inputs that drive future outcomes. Lagging indicators are backward-looking, reporting results after they've already occurred. Leading metrics guide operational action. Lagging metrics evaluate whether that action worked. In healthcare, hand hygiene compliance and staff training completion are leading indicators. They predict whether infection rates will rise or fall. The infection rate itself is lagging because by the time it climbs, the problem has already occurred. Tracking both gives teams a complete picture. The test is not time delay, it is causal direction. If a metric drives a future outcome, it is leading. If it reports what has already happened, it is lagging. A readmission rate reported with a 1-month delay is still lagging because it describes a past event. An appointment no-show rate is leading if it predicts a future revenue shortfall. A mature performance dashboard always includes both types. Leading indicators allow proactive intervention before outcomes deteriorate. Lagging indicators confirm whether that intervention produced the desired result. Neither alone is sufficient. Together, they close the loop. Question 49. A trial finds that a new blood pressure medication lowers systolic readings by an average of 2 millimeters of mercury with a p-value below 0.05. Reviewers point out that even though the result is statistically significant, the change is too small to matter for patient care. Which concept best names this distinction? Your options are A. Statistical bias caused by improper sampling. B. A type 1 error in hypothesis testing. C. The contrast between statistical significance and clinical significance. D. A confounding variable hidden in the data. Which one is it? Pause the video if you need more time. The correct answer is C. The contrast between statistical significance and clinical significance. C is correct because statistical significance and clinical significance are separate concepts. Statistical significance means the observed effect is unlikely to be due to chance, while clinical significance means the effect is large enough to matter in practice. A 2 mm drop can pass statistical thresholds yet fail to change patient care meaningfully, illustrating the gap between the two ideas. A is wrong because statistical bias refers to systematic error in sampling or measurement, not to the size versus significance distinction. B is wrong because a type 1 error occurs when a true null hypothesis is wrongly rejected. The result here is real but small, which is not a type 1 error. D is wrong because a confounder is an external variable distorting a relationship, not the difference between statistical and clinical significance. Statistical significance and clinical significance are related but distinct ideas. Understanding the difference is one of the most important judgment calls in reading healthcare research. Statistical significance asks whether an observed effect is likely to be real, captured by the p-value. Clinical significance asks whether that effect is large enough to change what you do for a patient. A result can satisfy one criterion without satisfying the other. Imagine a trial of 10,000 patients that detects a 2 mm of mercury drop in blood pressure with a p-value below 0.05. The result is statistically significant. Chance is an unlikely explanation. But a 2 mm drop falls well below the 5 to 10 mm threshold considered clinically meaningful, so the finding does not change treatment decisions. A disciplined reviewer always asks 4 things. How large is the effect in interpretable units? Is the p-value small enough to rule out chance? Does the magnitude exceed the clinical threshold? And does it change a treatment decision? Only when all 4 answers are affirmative should a finding drive practice change. The classic exam trap is treating a small p-value as automatic proof of importance. With a large enough sample, even trivial effects become statistically detectable. Always pair the p-value with effect size and clinical context. Modern reporting standards require both. Question 50. A health services researcher wants to ensure that subgroup-specific patterns are not hidden when a population is sampled. The researcher divides the population into homogeneous groups before drawing the sample. Which analytical technique is this? Your options are A. Stratification analysis that divides a population into subgroups before sampling. B. Predictive modeling that forecasts future outcomes. C. Factor analysis that reduces data complexity by identifying key variables. D. Meta-analysis that combines findings from multiple studies. Take a second. Which answer would you pick? The correct answer is A. Stratification analysis that divides a population into subgroups before sampling. A is correct because stratification analysis divides a population into homogeneous subgroups, such as by age or comorbidity status, before sampling so that each subgroup is appropriately represented. The technique improves precision and exposes patterns that would be obscured if the population was sampled as a single block. Stratification supports both research design and analysis. B is wrong because predictive modeling estimates probabilities of future outcomes for individuals and does not address subgroup sampling. C is wrong because factor analysis reduces the number of variables in a dataset by identifying underlying factors. It is unrelated to subgroup sampling. D is wrong because meta-analysis pulls published study results and is not a sampling technique inside one study. Stratification is a fundamental technique in research design and analysis. It works by dividing a population into homogeneous subgroups, called strata, before sampling or examining data. Stratification serves 3 core purposes. It improves precision by reducing within-group variation, It exposes subgroup-specific patterns that a pooled analysis would hide, and it ensures appropriate representation of every important category in the study. In stratified sampling, the population is split into strata that are internally similar on a key variable, such as age decade. A separate random sample is drawn from each stratum, so the final study sample accurately mirrors the population's subgroup structure. A classic exam trap is confusing stratification with risk adjustment. Stratification reports separate results for each subgroup, preserving that detail. Risk adjustment produces one combined estimate that statistically controls for group differences. Choose stratification when subgroup patterns are the answer you need to deliver. When a question stem describes dividing a population by a characteristic before sampling or analysis, or asks about subgroup-specific insight, that is the signal for stratification, not simple random sampling and not risk adjustment.
You have reached the end of our first question set. For the free complete exam preparation, visit our website link in the description, where you find thousands more practice questions and comprehensive study guides. Thanks for studying with us today. See you in the next video.